Okay? Transport and distribution. The hormones themselves. Are we clear with this? Because I'm going to talk. I'm going to introduce, and I'll let you guys take a little break. But I want to just start this off a little bit as an introduction over here. Are we clear with this? Okay. Like I said, it's all recorded, so you get to see it again. Now, let's talk about the hormones. When they get into the bloodstream, what's happening there? How they're being distributed. Well, they could either be distributed freely, just by the hormones themselves. They could just flow through the bloodstream, or sometimes they could be attached to proteins and not be utilized until it's necessary. The good example I use on this is that kids go into school. Some of them can walk to school on the streets. Some of them can ride on buses. When they get to the school, and it's cold outside, who do you think are the first ones that are going to go inside the school to get warmed up? The ones that are freely walking, or the ones that are in a nice warm bus? The freely walking ones, right? So the ones that, so what I'm saying here is that the free hormones are getting used up first. The ones on the buses or the ones on the proteins, those are on reserve. Okay? That's basically what they're saying here. So the free form, all right. That's a donut. Does a donut have a hole? No. That's not, you're looking at this, right? That's not a hole. Let me ask you this. If I take a knife or my finger and I jab it right through here, does a donut have a hole? Yeah. Oh, see, there's a difference now. Right? If there's a window in the wall up there, would you say that the wall has a hole in it? No. If I take a shotgun and blast a hole, there's a hole. So this is more or less like a window. We're not going through the cell. Does that make sense? We call this a fenestra. Now, if I extend this, you guys are going to go home to your family and say, donuts don't have holes. What are you talking about? So if we just extend this a little bit, what I'm actually drawing over here is the lining, the epithelial lining of a blood vessel. And think of this as a sheet, but then you curl it. So it's like this, what I'm showing here, but then we're curling it around so that we are making a blood vessel. Does that make sense? And a blood vessel has fenestra in it, little windows, to allow certain things to go through, in and out. They're not big, they're only going to allow certain things. Then you also have other ones that can go, so things can go through here, or if it's made properly, it can actually go through into this layer here. Now, keep in mind, that's a top view, but we have seen what it really looks like a few courses ago. Remember the good old days? Lollipop with 2 sticks? That's a phospholipid bilayer. This is going to be extracellular fluid. This is going to be intracellular fluid. Certain things can come through here, certain things can't. Inside, so there's water over here, and there's water here. Do you remember that? Inside here, it hates water. It's phospholipid. These are lipids here, these little sticks. Well, the lollipops themselves are what we call water-soluble, phosphorus. Right? So up here, it likes the water. In here, it doesn't. So we can have certain things go through that membrane, things that don't like water, fatty stuff, lipids, can pass right through here because mix oil and oil together, it can pass right through there, it can mix. But water-soluble stuff won't be able to do that. You have a water-soluble thing, it's going to ricochet right off. Because that water, not water molecule, but water-soluble hormone, when it gets in this area, it's just going to come right back out. Because it doesn't like water. So what I'm trying to show you, and we'll get back to this after the break, but what's going to happen here is that lipid-soluble hormones can pass right through here. If water-soluble stuff want to get in there, they have to have another mechanism, which I'm going to talk about, or they're going to go through the fenestra, because there is nothing here that's going to prevent water-soluble products to get in. Does that make sense? Okay? And like I said before, is if a hormone is bound to a protein, if a child is bound to a bus, that child can still come off. It's not irreversible. We're going to glue them to the bus and you can't get them off. So it's just, they're there for a reserve. Now, a little side note on this is that if you have kidney disease and proteins, which proteins should not do this. If proteins spill out in your urine, you should not have proteins in your urine. But if you have a disease, it can do that. If you lose proteins, you're also going to lose proteins that have certain hormones on it. Now think about this. You have kidney disease, you're losing proteins, you're losing hormones attached to the proteins, and maybe some of those thyroid hormones are attached there. You could see that you're going to lose thyroid hormones in the urine, and that person's going to have low levels of T3, T4. So some medical professionals might not put things together and say, whoa, you got low T3 and T4, we're going to put more of that in you. And we'll also try and figure out what's going on with your kidney. But if you're going to fix the thyroid issue, does that make sense? Okay, that's where you got to put things together. Okay, so this is hormones and the target cell interaction. So again, what we're dealing with here, the key is the hormone. The key hole is the receptor. And that's what we're dealing with. And it works similarly where it's a locking key. Okay? Now, we have crazy words here. Ligand. All that means is anything that binds the receptor. It doesn't have to be a hormone, it can be anything. But we got to throw in these anatomical words and chemical words for you guys. Whenever you see that, if you're using your book, if you want to use that, we're going to use the word ligand. That's all it is just something that attaches to a receptor. A hormone is a ligand. A key is a ligand. Okay? And the receptor itself is the binding site of that ligand. All right? So you put it all together, and you're going to have this ligand binding site when it's all together. All right? Just pretty easy terms for you to understand. Okay? But it's very specific. For instance, a growth hormone cannot get into an oxytocin receptor. It has to go into a growth hormone receptor. They fit like a locking key. All right? This won't fit into this. There's the hormone, there's the receptor. This is the only one that's going to fit like a locking key. It's very precise. Okay? Now, the target cells, very specific receptors, as I said, they're the keyholes, so to say. And we can have something called upregulation and downregulation. So this is what's happening. Think of yourself inside of a cell, okay? And you need glucose. Just bear with me. I know we didn't talk about insulin and stuff, but just bear with me. So this is what's going to happen here. You need glucose. So the thing that's going to allow glucose to come inside is a hormone called insulin. Insulin doesn't come inside the cell. Insulin is going to be a key to open up the keyhole to allow the door to open. You're inside of a cell. You're inside of a cell. There's the bloodstream. I have the key, the insulin key. There's the receptor. That's the keyhole. You're starving. You need glucose. There's tons of glucose out there, but it can't get inside unless the insulin key opens up the door to allow the glucose to come in. That's how insulin works. And we'll talk more about that when we get into diabetes. Okay? But you're inside here, and you need glucose. So this is a problem. You don't know what's going on out there. Maybe there's insulin out there, and the insulin doesn't see your receptor, doesn't see the keyhole. So what you're going to do is that, and I'm just giving you numbers, maybe there's only 5 keyholes out there, receptors for insulin. So what you're going to do is make a bigger net. Your cell is going to make more receptors for insulin. Instead of 5 receptors, you're going to make 100 receptors, hoping that the insulin out there is going to see now 100 receptors, is going to be able to see that better. Does that make sense? That's what we call upregulation. You're going to upregulate. You're going to make more of those receptors. You're going to make that cell more sensitive to low hormone. You know, maybe there's only a few different insulin out there. We're going to help you by putting more receptors out there so that you could glue on to us. Does that make sense? That's upregulation. Now all the sugar and all the glucose came in. Now the cell doesn't need all that glucose. So what is it going to do? It's going to take those receptors, and it's going to, they're made of proteins. They're going to come back into the cell, break it up into amino acids, and you're going to do what we call downregulate. We got enough glucose. We don't need any more insulin opening up the doors. Does that make sense what upregulation and downregulation is? And that, I forgot, Tyler, that's basically what's controlling this negative feedback. To control how much of this insulin or this hormone per se is going to be sensitive or not sensitive. Okay, so it's really responsive of the cell itself, what's happening inside. Okay, clear with that? All right, so let's talk about these receptors of hormones. Okay, now receptors for catecholamines. Ooh, that's a fancy word for a group of chemicals. Good examples of this is epinephrine and norepinephrine. Epinephrine and norepinephrine are a group of things called catecholamines that you're going to see quite often. Okay, so catecholamines and peptide hormones, these are either small hormones or water-soluble. I'm sorry. They're either large hormones or they're water receptor or water-soluble hormones. They can't get into the cell. Catecholamines. Okay? They are kind of like this. That's a catecholamine, like norepinephrine, epinephrine, or certain peptide ones. This cannot get into here because it's water-soluble. Right? We just explained, if it's a lipid soluble, it passes right through here. If it's water-soluble, it can't. Or if it's a big one, it just can't because it can't squeeze through here. So if it comes, it'll just ricochet right off of here. So these receptors are connected and have to attach itself to something that's going to be outside the cell. It's going to be a receptor that's made in the cell membrane. Does that make sense? So its receptor is going to be on the membrane itself. This is going to, when this attaches to this, it kind of changes shape, does a brigade of things that we'll talk about, and then it tells inside the cell what to do. All right? ECF, extracellular fluid, ICF, intracellular fluid. So inside the cell. Is that clear?
catecholamines are either water soluble
or large molecules.
wait, say that again.
Catecholamines are just specifically epinephrine and norepinephrine. But catecholamines and peptide hormones kind of work similarly in where the receptor is. Okay? They could be, like I said, they could either be water soluble or they could be large molecules. Either way, they can't pass through here. So its receptor has to be outside the cell. All right? Then we have thyroid and steroid hormones. These are lipid-soluble hormones or very small hormones. These are ones that can pass right through here to look for its receptor. Its receptor is going to be someplace in the cytoplasm or keep in mind that there's a nucleus here. And the nucleus itself has a nuclear envelope. And that nuclear envelope is the same thing as a phospholipid bilayer, but has two of those layers. So it works the same way. If there's something that can pass through here, look for its receptor. It is not in the cytoplasm. It can easily pass through the nucleus too. And look for its receptor inside the nucleus. Does that make sense? Did a color coding. So water-soluble hormones and large hormones, its receptor will be someplace outside the membrane or on the cell membrane itself. Fat or lipid-soluble hormones or smaller hormones can squeeze right through here, look for its receptor in either the cytoplasm, and if it's not there, can pass through the nuclear membrane and find its receptor inside the nucleus. Is that clear? See how it's colored? This is my art therapy. All right? As opposed to me just verbalizing things to you. All right? So they work similarly on that. Now, classes of receptors. Just reiterating on this. The membrane-bound receptors, that's here in red, they're going to be integral proteins. Proteins that are going to be going through the whole membrane itself, but it's a part of the membrane. These are for hormones that cannot enter the cell. They interact with ligands that are water-soluble or large. This involves what we call a second messenger system. We're going to get into this. It's probably the hardest part of it all. When this goes, this hormone is referred to as the first messenger. We don't call it the first messenger, but that message has got to get someplace inside here. The message, not the hormone, the message. So it's got to get the message into here. So there's going to be a brigade of stuff that goes on to get that message inside the cell. This attaches here, it kind of changes shape, a brigade of things happen here, and then a second messenger that just got it is going to be in here. We'll go through that. I got a little video to show you. Okay? It's a chain reaction that happens. And the ligands are water-soluble or larger ligands. Protein hormones, polypeptide hormones, catecholamines, the things that cannot get through that cell membrane. Just like that, like what I showed you. There's our phospholipid bilayer, and there's our membrane-bound receptor. Then we have receptors that are found intracellularly, right? Inside the cell. The green. It's It's either in the cytoplasm or the nucleus. These are for hormones that can pass through that phospholipid bilayer. The ones that we're talking about is the steroid hormones, hormones like testosterone, estrogen, progesterone, the ones that end with "one." All the adrenal cortex ones also are going to do that. Cortisol, aldosterone. And the thyroid hormones, the ones I showed you before as T3 and T4. And they could pass right through that phospholipid bilayer, find its receptors someplace inside the cell. Now, let's focus on the membrane-bound receptors. These are the most difficult and challenging for students and for myself to teach. So I'm going to explain that to you. I'm going to go for the hardest and work our way down to the easiest for us to explain. We have two ways that the red, and we're just talking about the red now. Forget about the green. We're just talking about the membrane-bound receptors over here. We can either do a cascade of events that involves something called a G protein, or one where it doesn't involve a G protein. And it tells a second messenger someplace inside the cell what to do. So let's talk about the G proteins first. Now, this is the most advanced, this is the most complex one. I have a few different ways of teaching it. I'm going to verbalize it here first for you. I'm going to show you a picture. I'm going to give you an analogy with a nightclub, and then I'm going to show you a little short video for about a minute or two. I'm hoping that one of those are going to click. Okay, but there's a lot of words in here and it's dealing with chemicals and stuff. Okay, so if you want, and it's a good time, put the pencils down and just listen. And one of these will click. I mean, if you want to write stuff, that's fine, but you know, I got in trouble once before. They said, my teacher says I can't write stuff. I'm recommending you not to write anything. Everything is recorded. Everything is on the PowerPoints. Okay? All right, so let me verbalize this first, and I'll give you my little scenario, and then I'll show you the picture. So what's going to happen here is this. Cascade events. To give you an example, that we're going to increase something called CAMP, which is cyclic adenosine monophosphate. That's what the message is in here we got to do for this particular hormone. I'm just giving you an example. So this is what's going to happen. Our hormone is our first messenger. We never refer to it as a first messenger, but we do refer to something else as a second messenger. You need to understand, well, that is the first messenger. So the hormone needs to get its message into the cell, but it can't get into the cell physically. So how does it go about doing this? Well, the hormone is going to attach itself to the membrane. Okay? Then what's going to happen is it's going to bind to this G protein, which is located in the membrane itself. A protein is referred to as the G protein. The G protein is going to be activated. They don't explain this. The G protein has something on it called GDP, guanosine diphosphate. And when it gets activated, there's a GTP that's inside the cell that knocks off the GDP. GTP is guanosine triphosphate. It has 3 phosphates on it. So the G protein gets activated, the GTP gets knocked off by GTP that now attaches to the G protein. And now as it's activated G protein, it's going to have another enzyme that's going to be inside the membrane called adenylate cyclase. If it ends with ASC, it's an enzyme. That gets activated. Once it gets activated, it's going to produce something called CAMP, cyclic adenosine monophosphate. This is the second messenger. This is the message we need to get inside the cell. How it knows to be activated, it's from outside the cell going through all these steps. CAMP then binds to protein kinase. Again, another enzyme, ends with ASC. Protein kinase causes phosphorylation on certain proteins. This needs ATP to occur. ATP is energy. It needs energy for that to happen. It's then going to activate proteins of whatever that hormone was supposed to tell it to do. And I'll explain what this is in a moment. So let me just explain to you what this is all about. Let me give you an analogy of a nightclub that I've been using for a number of years, and it seems to work out. Let's say I want to go to New York City, and there's tons of nightclubs down there. One I want to go to is something called Catacombs. Okay? Now, I'm the hormone, and I want to go in to see the show at the nightclub. So I'm going all over New York City, and there's tons of receptors, there's tons of nightclubs. I need to go to a specific one, a lock and key. I'm going to go to Catacombs. I finally find it. So I said, this is it. I made an attachment. It's right here. But I can't get inside. Okay? Now, the reason why I can't get inside is because there's a big guy that's right in front there, and he's got a big G on his shirt. And it's not for Gamaro. It's for G protein. Okay? So I can't get inside. Now, the only thing about this analogy is that even though I'm the hormone, I'm not supposed to go inside. That's the only thing I got to try and figure out what I want to do with the analogy. But the message is I want to see the show. Okay? But I can't get in because there's a big G protein, right? The bouncer's there, the big G. So he's got to, I'm saying I want to get in. So he's got to change shape. He's got to get activated by turning around and opening the door. You see what I'm saying? So he's got to change shape to do that. He opens the door, and inside, there's the maitre d' there. He's got to call the maitre d'. So adenylate cyclase is the calling. You've got to call the maitre d'. The maitre d' is there, and it just happens that this maitre d's name happens to be Camp. Go figure. So his name's there, Camp. Now, he's the second messenger. I want to get a good seat. He's going to take me to a good seat. But I got to do something before. What do I have to give him so that I get a good seat? Right. See, I got to duke him, right? I got to give him like a 20 bucks. So it's costing me to do that. ATP. It's costing me energy. It's costing me something. So I give him the 20 bucks, and then he takes me to a great seat, and I see the show. That's the whole thing that I want to do, is be able to see the show. The goal. Does that make sense? Let me show you a picture, and I'll explain about this rapidly thing in a moment. But this is the picture. And look what's happening here. Here's the hormone, the yellow. It can't get inside. So what does it do? It binds to the receptor. This is going to change somewhat of shape. Here's your G protein. When this changes shape, this activates the G protein so that GTP comes on, GDP comes off. Now GTP is attached to this, and this is now going to activate this enzyme, adenylate cyclase. When this gets activated, utilizing ATP, it's going to produce a lot of CAMP, cyclic adenosine monophosphate. Once this comes pouring out of here, it's going to activate protein kinase and do whatever it needs to do. So this hormone is wanting to do this yellow thing here, but it has to go through all these steps to get that message across. Is that clear? Let me show you the video.
Epinephrine is one of many hormones that is water-soluble, hydrophilic, and therefore unable to cross the hydrophobic plasma membranes of its target cells. Instead, it binds to receptor proteins located in the plasma membrane and does not enter the cell. When epinephrine binds to beta-adrenergic receptors on the liver cell, G proteins on the inner side of the cell membrane are activated. Each G protein is composed of 3 subunits, and the binding of epinephrine to its receptor protein causes one of the G protein subunits to dissociate from the other 2. The G protein subunit which dissociates from the others carries a GDP, which is replaced by GTP when the subunit is activated. The activated G protein subunit then diffuses within the plasma membrane until it encounters adenylyl cyclase, a membrane enzyme that is inactive until it interacts with the G protein subunit. When activated by the G protein subunit, adenylyl cyclase catalyzes the formation of cAMP from ATP. The cAMP formed at the inner surface of the membrane diffuses within the cytoplasm, where it binds to and activates protein kinase A, an enzyme that adds phosphate groups to specific cellular proteins. In liver cells, protein kinase A phosphorylates and thereby activates another enzyme called phosphorylase, which converts glycogen into glucose 6-phosphate. The glucose 6-phosphate is then converted to glucose. Through this multi-step mechanism, epinephrine causes the liver to secrete glucose into the blood during the fight or flight reaction.
Making sense? That's probably, I'll be honest with you, that's probably the hardest part of all endocrinology for me to understand. Not saying anything else is easy, I'm just saying everything else is like there's a lot of hormones. You're overwhelmed by the volume, but this is very conceptual. And I think that's probably the hardest thing for you to actually understand. All right? Questions about that? No? All right. So this is just showing the same thing, just another picture in words over here and follow numbers. It's the same thing. Okay? Now, let me go back to this for a second. This part here, which I kind of skipped over, this is all the steps, and this part here. Why does, for hormones that are water-soluble and large, peptides, epinephrine, norepinephrine, they happen to go very fast, though, during this whole process. Even though it's a long cascade, it happens very fast. The reason why is because you've got to visualize that this receptor is bound to, you got to think 3-dimensionally. There's a G protein here, there's one over here, there's one in the front, there's one in the, does that make sense? You got to think 3-dimensionally. So what's happening here, there's the receptor, it can activate 3 different G proteins or more, depends, I'm just giving an example, and each one of those could do, you see how it's getting, it's compounded. So even though one hormone's over here, the process could happen so rapidly because it could activate many things at the same time. Is that clear? So hormones that are epinephrine, norepinephrine, their responses are very quick, even though there's a big cascade of events. Peptide hormones happen quickly because of this amplification that happens over this cascade of events. Okay? All right. Other second messengers. I just gave you an example of CAMP. But there's a lot of other second messengers that do other things. Now, I am not going to hold you in this course to understand those other mechanisms. It's pretty detailed, and it's a lot there. It's enough to keep you busy. You need to understand CAMP and the way this works is because that's how pharmacology works. We can actually block G proteins, or we can accelerate G proteins. And that's how certain medications do. When you get into pharmacology, you'll be learning about the G proteins again, or at least just review. But that's where it's going to come up again. That's why I got to teach that, because I know most of you are going to take some sort of pharmacology in your future classes. Okay? Even for radiology, because you got to learn about radiotherapy, right? In that way, some sort of medication. So, but these are other second messengers. Not going to hold you to know those mechanisms. However, I do want you to know the other names of them. I'm not going to ask you to write them out, but I might say all the following are second messengers except. You should know what they are, okay? So understand the CAMP's mechanism, as I showed you just with all those different scenarios. But don't worry about the mechanisms of the second messengers. Just know what ones they are, okay? If you're really inclined to know a little bit more, then you can look at the other diagrams that I have up here, but I'm not going to hold you to remember them. Just showing you what's going on here, it looks pretty much the same. There's the receptor, there's the G protein, but instead of making CAMP come out, you have this something called IP3 as the second messenger. It's the same way as using my analogy. We go to, I want to go to that nightclub. I want to go to catacombs. The G protein, the bouncer's still at the same place I'm at. But this night, when he opens up the door, the maitre d's not there. But in this case, it might be my brother who owns the place. He's the owner. So now he's the second messenger. So everything up to that point is still the same, but now it's my brother. And in this case, he's going to take me a different way to get a good seat. Maybe he'll take me up on the balcony, but I don't have to duke him. He's my brother. I'll slap him silly and I'll tell my mom. All right? So it's a different mechanism from then on. Maybe another day I go and it's the manager, and the manager says, "Oh, you're John's brother. Don't worry about it. But I'm going to take you down through down the cellar to get up to that spot over there. But you don't have to duke me or anything." Does that make sense? So up until that point, it's going to be the same, but the second messengers are different. Okay? And this is showing you another one. The second messenger. Well, here's IP3. Let's do with that. Okay? All right, and this is more detailed. If you want to know a little bit more about G protein, it's got alpha units or subunits and beta subunits. You don't have to go into so much detail about that, but this is a little bit more detail should you need to go into there. Okay? Now, these are the hormones that do what I just showed you. You don't have to memorize them. I'm only putting this up here to be complete. These are all the hormones that use the G protein. Just for yourself to understand which ones are there. And in essence, it's all catecholamines, epinephrine, norepinephrine, all peptide or protein hormones do this. What are soluble? Okay, or large molecules. And these are the second messengers. The list of those. Again, you don't have to worry about the mechanisms of them. Okay? Now, we're going to get a little simpler now. The hormone that is water-soluble cannot go through here. So its receptor is going to be someplace on the membrane. There could be a G protein here, and that whole thing I just explained to. Or, in certain hormones, they attach to a receptor that doesn't have a G protein here. That there isn't a bouncer to the nightclub. That you could just walk in and see the second messenger right there. Does that make sense? So it's pretty much the same, we just don't have the bouncer, we just don't have the G protein. And certain hormones do it that way. So this is simpler because the G protein is not included with this. Okay? And it's pretty much basically the same type of thing, okay? And this is also very rapid because it's the whole cascade, the way I kind of show you. Push this button and it kind of tells other things what to do. So it's basically this. There's no G protein. So now I have the G protein being the connection between the adenosine denylate cyclase and the receptor. This is attached to the, well, now it's guanylate cyclase. And there's no G protein there. We're just skipping the bouncer. Does that make sense? Simply. Okay? And these are the hormones that do that, with insulin included on there. All right? Again, I won't ask you about this. It's really just being complete. There's just too much of those ones you list for you to know. Because the biochemistry, you'll get to know more of that stuff if that's what you want to do. But just putting it there just to be complete. So if you know it as catecholamines and the protein or peptide hormones, that's good. Okay? Questions about that? All right, now, let's talk about the opposite now, or the other one. So we're done with the red here, that could use a G protein or without a G protein. Now, let's talk about the lipid-soluble or the small hormones that can pass through here and look for its receptor either in the cytoplasm, if it's not there, it can pass through the nuclear envelope and look for its receptor in the nucleus. This one's even more simple, or more simple. I'm not going to read this all to you. I might as well just show you the picture. Let me orient you. Here's the cell membrane, the phospholipid bilayer. That's this. Okay? Here's all the cytoplasm. Here's the nucleus. And here is the nuclear envelope. Keep in mind, the nuclear envelope is the same architecture as the cell membrane. The only thing is, it's two phospholipid bilayers there. We need to protect the stuff inside the nucleus better than just inside the cell. Does that make sense? But if it can pass through here, it can pass through here. This is phospholipid bilayers. So what's going to happen is this. This steroid hormone can easily pass through the cell membrane, look for its receptor in the cytoplasm. If it finds it, super. If it doesn't, it's going to go further and go inside the nucleus. It looks for its receptor. This receptor is attached to what we call chaperone proteins. Okay? Chaperone molecules. Once this binds on here, the chaperone molecules, which kept this inactivated, come off, and now you've got this receptor hormone complex. It then binds to someplace on the DNA at certain protein. It goes through transcription to make the mRNA. That goes outside here. It goes through translation. Do you need me to go over transcription and translation? You understand that that's to make a protein. And that makes it new protein. So that message is telling the cell to make this. It has to go through this. Okay? I'm not going to ask you questions about transcription and translation. I assume you already did that.
Steroid hormones are not water-soluble. They travel in the blood attached to protein carriers. When steroid hormones arrive at their target cells, they dissociate from their protein carriers and pass through the plasma membrane of the cell. Some steroid hormones bind to specific receptor proteins in the cytoplasm and then move as a hormone receptor complex into the nucleus. Other steroids travel directly into the nucleus before encountering their receptor proteins, not shown. The hormone receptor protein, activated by binding to the hormone, is now able to bind to specific regions of the DNA. These DNA regions are known as the hormone response elements. The binding of the hormone receptor complex has a direct effect on the level of transcription at that site. Messenger RNA, mRNA, is produced, which then codes for the synthesis of specific proteins.
But because this steroid hormone has to go through here, look for stuff not there, look over here, and lo and behold, it comes here. There isn't amplification either. It just goes onto one receptor, and that complex goes on here. It doesn't get amplified. So hormones that utilize this, the steroid hormones and the T3 and T4, happen to be making its products much slower than what I showed you in red over here. Does that make sense? Because it doesn't get amplified. All right? So no amplification. That's what I'm saying. So that's why it happens slowly. Sound good? And these are the hormones that do that. The sex steroids, which I mentioned a few on there, testosterone, progesterone, estrogen, all the ones that come from the adrenal cortex, which you're going to find out soon enough, aldosterone, cortisone, and androgens, which are basically sex steroids, and the thyroid hormones. So those are the ones that do that. Okay?